Okay, so we're going to start with the first graph that you should be pretty familiar with right now, the parabola. So I'm going to quickly jot these points in. Now, the scale here is half units, so it's actually going to be, the first one's going to look like this, and then at 2, be at 4, and one more, so at 3, up at 9, and roughly, oh, I got to do that again. That was a terrible parabola. Okay. Oh, that's why. That's why. I'm off by just a little bit here. Again, none of these are my fault. This is a Dayquil or Sudafed or whatever it was that I got this morning before I went off to work. There, that looks more like a parabola. And kind of like that. Okay. So we're going to take a look at this transformation. So I'm going to show you on the graphing software. So just a second here. So to start, it's y equals x squared. Okay, there's our original graph. So what do you think is going to happen when we do these two transformations here? Maybe give me one of them? Sure, Connor?
Horizontal stretch factor of 1/2.
1/2, yeah. So we're going to see this graph get half as wide. Anything else? Yes, Lily?
2 to the right.
2 to the right. Okay, so there's these two pieces here. Let's compare it and see what happens when we put it in. We end up with 2x minus 2. And now we are at half as wide, but it only actually moved over 1. So it's a tricky thing to notice. The easiest way to see it is down here. Here's 0, right? And then here's the point at 1 right here. So it's actually only moved 1 unit over, which is kind of strange. Now, one reason that we got to, it's hard to see it this way, is it hasn't actually been factored out. So the way you always want to deal with a transformation, before you do anything or say anything about it, you should always factor out whatever's in front of x. So we should write it like this before we talk about it. And now you can see in factored form that this minus 1, you'd probably be more inclined to say 1 to the right. Okay? So let's plot this and then we'll take a look. So, whoops. It's there. Okay, so here 1 over okay, and then the last one should look like this. Okay. So let's just recap what we had mentioned happened here is, first of all, we saw that the graph, it actually only moves over by 1 to the right. And if we wanted to take a look at, verify that it's still a half, well, maybe, for example, if I took the distance here, this distance is 2 units. In this graph here, this distance is only 1 unit. So if I take the same set of points, they're half the width, so they're no longer twice as far apart. So we could write this in as the graph has been shifted 1 unit to the right, and a stretch factor of 1/2. Okay. So the reason I always start with this example is to remind you of this one thing that can cause careless mistakes. If you don't factor out, you're not going to see the proper translation. So what you want to do is every time there's something attached to x, you're going to want to factor it out. And we'll practice that a lot this block. but the easiest and most, friendly way to look at it in standard form that we've been talking about is the horizontal stretch factor appears here like this, where it's factored out. Okay, so keep that in mind. In transformations, this is what we're going to work with. This is the order that we're going to use. Now, if you notice, it's very similar to what you already know from your other order of operations. If we're talking about this kind of stuff, we're talking about multiplications. We're talking about this stuff. We're talking about additions and subtractions. So it is the same order of operations that you already know, but there's a different language to it in transformations. So I like this keyword rect. It's not really a word, I guess. Is it a word, rect?
I don't know.
But anyways, it helps you to remember, first we're going to do reflections, then expansions, compressions, translations. It's kind of like when you say bed mass in grade 8, right? You probably never say bed mass anymore, but there was a time when that was helpful to remember your order of operations. Okay, so let's see how that works. In this table, what I've done for you here is I've actually split it up as reflections. This would be my expansions and compressions and translations. So the table is in the order that we should be doing our transformations. So when we describe it, we'll be describing it in the right order. Okay. So in the first one, what will we have for reflections? In English, can someone give me a description?
You're reflecting on the x-axis?
That's correct, yeah. So this is an x-axis reflection. Okay, can somebody give me maybe a stretch factor? Sure, go for it.
0.
Oh, you're so close. Not quite 0, right? 0 would mean that the whole graph disappeared,
Okay.
right? So 1 meaning that there was nothing affecting it. If you don't want to be so technical about it, you could just scratch it out and say, don't worry about it, because technically it's not there, but it would be a 1 if we gave it a number. Okay? Horizontally? Yeah. And translations? In one shot. 5 where?
Right.
Okay, so we'll just go like this. 5 right and
4 left.
4 up. Yeah. Okay, so remember, as I mentioned, the easiest way for you to see the transformation happen is when you take out the horizontal stretch factor. So before we do anything to this next one, we should start in the margin here by rewriting this. Like that. I factored out the horizontal stretch factor. Okay. Because you might be tempted to say that there's been a translation 6 units to the right. That's not correct. It's actually only moved 2 units to the right. Okay, so I'm going to let you continue those next 3 questions. Fill in that table or into your own notes and come up with how this graph has been moved. Okay, so I'll fill in this one here, and then I'll ask someone for some help in the next part. There's no reflections happening. There is a vertical stretch by 2, a horizontal by 1/3. We go 2 to the right and up by 5. Okay. In the next one, if you factored this out properly, you should have negative f. Now the negative sign needs to come out too. That also affects the way the x-coordinate's going to be changed. So this is going to be x, let's see here, plus 3. Okay, so let's see now. If I was to do this, well, this is a good one. The reflection is in both axes. Do I have anything vertical that's going to change for the vertical stretch factor? Nope, so that's just going to be a 1, or you can cross it out. So we can just say not important. What about horizontally? Half, good. And tell me about the translations.
3 left.
Yep. And 1 up, excellent. Okay, so we're pros at this. The last one is just see how you're doing with this business of factoring, because there's a fraction in there. I don't know why, but sometimes fractions, it's just like something in your brain goes boop, and it doesn't work. So fractions tend to freak people out. That's why I figured we'd practice one with fractions. So what would you have this time? Should be a 6. So if you're wondering, like some people work backwards, and they try to figure out, like what number goes here to get back to -6, and they figure, okay, -2 times 3 is -6. But when you're factoring stuff out, you're really just, can someone close that back door? Thank you. When you're factoring something out, you're just dividing. So if you're wondering, how can you get these numbers quickly if you're not sure, all you have to do is divide this by a half, because that's what we're taking out of it. So whatever the number is, you can just divide it and then you'll get it quickly. Again here, there's no reflections. There's a vertical stretch by 5, a horizontal by 2, 6 to the left, and 7 down. Okay. Any questions so far? Can you just show me with a 5 that says, Mr. Joyce, this is so slow that I'm starting to drool, and a 1 that says, I have no idea what you're talking about, I wish Mr. Kamosi was still here. Okay, good. I just want to make sure that I'm not going too slow, too quick. So in this one here, what we're going to do now is we're going to try and go from the math to the English. So see if you can figure out, how would you describe this with English words? What does it say? What does that math mean? Okay. There is a slight trick in the very beginning of it, but hopefully you can work around it and figure out what it means. So
do a barrel roll.
Most people started out, they caught on to, that I had a look on their sheets, they caught on to the fact that you could just divide by 2 and it looked like you normally expect it to. So by dividing by 2, this is more friendly, this is kind of the notation we've been working on. Then it's a little easier to see. If I was to say what's happened here, I could say that there has been a vertical compression of 1/2, a horizontal expansion of 4, and moved 3 units to the right. Now, there was some, I don't even know if this is going to be an issue here, but there was some question in the last block as to, so if I'm compressing by a half, compressing means smaller, but a half is small, so shouldn't it be twice as big? And everybody in the class was kind of like, what? But to the people who were asking this question, they were kind of like, does compression in a half mean that you're actually getting twice as big? No, it doesn't. If you're not sure, you can basically cross these out. However you see it, just use the number. That's the number you've been given. That's the one that corresponds with what we've been calling the vertical stretch factor and the horizontal stretch factor. Okay, so if at any point there's some confusion in the linguistics of it, the numbers won't trick you. I won't be telling you that the graph has shrunk by a half, and then you'd have to interpret that as now it's twice as big because I shrunk it as a half. Don't worry about that, okay? The numbers you see are the numbers that I'm working with as well.